Hello, grade 9s. We are going to talk about today expressing numbers in exponential form. So just like we were able to convert between decimals and fractions in our rational numbers unit, and it didn't mean that the numbers were any different when we represented them in a different way. It was just a different way to express that same value. So an example could be 1/2. I can write that as 1/2 in fraction form, or I can write that as 0.5 in decimal form. So it was two forms of the same number. Well, when we're talking about powers, we can often represent numbers, not every number, but most numbers, as powers, or in more than one way. So one of the forms that we can write it in is called standard form. Now, standard form is almost exactly what you would think of it. It is the normal way numbers are written. So, like 5. How do I write the number 5 in a normal way? I just write 5. Or like 18, or 64, or 9, or 4, or 81. Those numbers, as is, that's the normal way we say numbers. That is a number in standard form. The other way we can sometimes represent numbers is in exponential form. And again, the name here kind of makes sense of what it is. Exponential form is a number when it is written as a power. That means I can write it with a base and an exponent. So like 3 is the standard way of writing a number, but 3 to the power of 1 is an exponential form of writing that. 4 is the standard way of writing a number, but 2 to the power of 2 is an exponential way of representing that number. Now, converting between the two forms can be useful and will be used for different things throughout the unit. So today's lesson is all about just converting back and forth between the two forms. Now, we're not going to look at every single number in standard form and convert it to every single way exponential forms can be, or every single exponential form of that number. But there are some really common powers. So kind of like we had like sight fractions, where that conversion between decimal and fraction, we wanted to have like straight away locked and loaded in our brain. So if we saw it in one representation, we can convert it to the other representation seamlessly. There are some powers that we also want to be able to convert between standard form and exponential form really quickly. Now, if you're taking a look at this sheet where you're like, oh my gosh, that's a lot of sight fractions, we can start by looking at a few of these and realize, okay, this one, we automatically know what it is and should not require any additional brain power. And that's anything that has a base raised to the power of 1 or raised to the exponent of 1. Right? These 5 on the page here should not be any additional brain power to you, because anything to the exponent of 1 is just itself. So 2 to the power of 1 is 2, 3 to the power of 1 is 3, 4 to the power of 1 is 4, 5 to the power of 1 is 5, and 10 to the power of 1 is 10. Now, if we're kind of continuing in that pattern, we should know our powers of 2 really up to 15 pretty well. But here I'm only expecting you to know 2 to the power of 2, 3 to the power of 2, 4 to the power of 2, 5 to the power of 2, and 10 to the power of 2 really quickly, locked and loaded in your brain today. Can you fill in those blanks? Pause the video, try it out. And welcome back. You filled in those blanks and you got 2 to the power of 2 was 4, 3 to the power of 2 was 9, 4 to the power of 2 was 16, 5 to the power of 2 was 25, and 10 to the power of 2 was 100. Now, automatically, if we take a look at our sheet, there's actually a lot fewer that we have to, use additional brain power to have commonly recognized in our heads. But it's a lot less than what we started with, and I just wanted to point that out. Now, going from exponential form to power form is actually pretty chill, because even if I don't know what it is off the top of my head, I can go ahead and write it as repeated multiplication. Now, I know we've already figured out the first ones, but I'm going to write those out as repeated multiplication anyways. So for 2 to the power of 3, that's my base of 2 being included in the repeated multiplication a total of 3 times. Right? 1, 2, 3. Something I'm just going to point out is that notice I didn't say it's multiplying by itself 3 times, because that language is not necessarily accurate. A number, let's say 2, multiplied by itself once is 2 times 2. Multiplied by itself twice is 2 times 2 times 2. Multiplied by itself 3 times is actually not 2 to the power of 3, it's 2 to the power of 4. That's why I never aim to say multiplied by itself when talking about powers. Instead, I'm always using the phrasing, it's included in the repeated multiplication 3 times. Because this 2, the base, is included in the repeated multiplication, right? That's multiplication. I could use a dot, I could use an X. But 3 total times. 1, 2, 3. That is a more clear way to explain how to write something out as repeated multiplication. So I just want to be really cautious about that language and point it out so that you can understand that difference. Okay, but back to this. 2 to the power of 3. I've got 2 times 2 times 2, which I get as 8. Now, if I'm noticing in my answers here, every single time I write an answer, it's just getting bigger, as if I multiplied my answer by 2 from line to line, which is exactly what I'm doing, right? Every single time in the repeated multiplication, I end up just multiplying my previous answer, let's say this was my previous answer, by 2 one more time. And that's very true if I keep on going, right? I took my previous answer, which was 2 times 2 times 2, and multiplied it by 2. So 2 to the power of 4, I know is 16, because 2 to the power of 3 is 8, and I just take that answer and multiply it by 2 one more time. And 2 to the power of 5 is just going to be that 16 times 2, which is 32. And that 2 to the power of 6 is just going to be 64, because it's 32 times 2 one more time. Okay. Can you take a moment, pause the video, and figure out the last ones for the power of 3s, powers of 4, and powers of 5? Okay, welcome back. I'm assuming you did it. Life is pretty great. Same kind of pattern happens when I take a look at 3s, except instead of multiplying my answers by 2 every time to get to the next one, I'm multiplying them by 3 every time to get to the next one. Right? This was 9, which means this guy's also 9. And multiplying it by 3 gives me 27. And in the same rationale, I could just take 27 and multiply it by 3 to get 81. But if you're like, man, I'm not good with my mental math there, I can also, with 27s, I can also go ahead and say, well, 3 times 3 is 9, which means this 3 times 3 is 9, which means 9 times 9 is 81. Okay, lots of ways to kind of process things, lots of ways to think things through, but I just want to talk about how we can get those, at least really quickly, if we don't happen to have them perfectly memorized in our heads. Okay, I'm just going to go through the next ones pretty quickly. So 4 to the power of 3, that's going to be 64. There's 5 to the power of 3, which is 125. Okay. What I want to point out about what's already on our page is a few things. Thing number 1, look at the commonalities between powers of 2 and powers of 4. Every second power of 2 actually is also a power of 4, which makes a lot of sense if we think about it. And I'm going to write them down here. You don't have to write this down. I just want you to kind of look and listen and absorb. But 2 to the power of 2 is 2 times 2. 2 to the power of 4 is 2 times 2 times 2 times 2. 2 to the power of 6 is 2 times 2 times 2 times 2 times 2 times 2. Now, we know that 2 times 2 is 4, which could then be written as 4 to the power of 1. Every 2 2's multiplying together gives me 4. So I'm going to replace every 2 2's with a 4. 2 2's, 2 2's, 2 2's, which means I can also write this as repeated multiplication with 4's, which means I could also write it as a power with a base of 4. Now, I will notice this pattern all of the time with 2's and 4's. So 2 to the power of 8 will give me 4 to the power of 4. 2 to the power of 10 will give me 4 to the power of 5. Because this pattern will always work. Every time I have 2 2's multiplying together, I can turn it into a 4. And if I have an even number of 2's, I could turn every pair of 2's into 4's, which means I'll have those commonalities. So something kind of interesting to notice. The other thing that I want to point out with those numbers is that if I'm looking at 64, I might in my head be like, okay, I know that that's 8 squared. I might now recognize in my head that that's 4 to the power of 3. And I might now also recognize it as 2 to the power of 6. And you might be thinking like, okay, if you give me the number of 64 and I'm asked to write it as a power, which one do I write it as? And that's a really solid question. A lot of the time throughout the unit, we are going to want to write a number in standard form into exponential form that has the smallest possible base. So, if I just go off to the side here and talk about the number 64. 64 we might already have loaded in our heads as 8 to the power of 2, or 4 to the power of 3, or 2 to the power of 6. How do I know which one to do it in? I want to take a look at the power that has the smallest base. This has a base of 8. This has a base of 4. This has a base of 2. This here is going to be your best option down the road because we are often wanting to express things in the smallest base possible, which will later help us reduce fractions or fractions of powers or division of powers. So 64, instead of you always thinking of it 8 to the power of 2, I want us to think about it as 2 to the power of 6. And I'll use this example on the next page of how we can convert from standard form to exponential form really easily. Okay. The last one, powers of 10. Powers of 10 are really awesome because powers of 10 are all multiples of 10. These are pretty easy to figure out because the exponent tells us the number of zeros in our answer of standard form. Now, we've already done 2 of them, but let's see what I mean here. I had an exponent of 1. I had 1 0 in standard form. I have an exponent of 2. I have 2 zeros in my standard form. The next one, I have an exponent of 3. I have 1, 2, 3 zeros. Anything as a base of 10 raised to some exponent is actually quite simplistic to put in standard form because this is always true. So 10 to the power of 12, that's a 1 with 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it is pretty straightforward if we could recognize that pattern all the time. Okay, now, on this page, we went with common powers that should be easily recognizable to us down the road, but we were converting everything from exponential form to standard form. And that's pretty straightforward, even if I don't have them memorized, because I could always rely on repeated multiplication if I had to. Now, I don't want to have to rely on repeated multiplication. I would prefer to have those locked and loaded in my brain because they are common. But sometimes we might want to write a number in exponential form and it's not a common power. And how are we going to do that? Well, that's a great question. I'm so glad you asked. We're going to do that using prime factorization. Now, prime factorization. Hopefully the word prime is shooting off fireworks in your head and you're like, "Ooh, prime, like a prime number?" And that's exactly true. Prime factorization has to do with prime numbers. Factorization has the word factor in it. And if you're like, "Whoa, factors," I know factors of a number, right? Like factors of 12 are 1 and 12, 2 and 6, 3 and 4. It's just ways that I can break down that number into smaller components that multiply to give me that number. And you would be right again. So prime factorization is a process in which we can express a number as a product of its prime factors. We can determine the prime factors by creating a factor tree. To make a factor tree, we replace each number with 2 or more factors that multiply to that number. We'll repeat this process until we're only left with prime factors. Now, I want to point out what a prime number is, just to refresh our memories. A prime number has exactly 2 unique factors. 1 and itself. 1, the number 1 is not a prime number because the only things that multiply to give me 1 are 1 and itself, which is also 1. Which means I don't have 2 unique factors. I only have 1 unique factor. So 1 is not a prime number. But some of the prime numbers that we know and we love are 2, because the only factors of 2 are 1 in itself. 3, because the only factors of 3 are 1 in itself. 5, because the only factors of 5 are 1 in itself. And then I can continue on. 7, 11, 13, 17, 19, 23, etc. Okay? But these ones here are our smaller prime numbers. Now, when we take a look at some of the numbers we're trying to write in exponential form, the first 3 examples I'm giving you are ones that you did not see on the previous page. So, these aren't ones that we'd have in our heads, but they're also pretty complex because it's not going to be a single power that we're going to get as our final answer. It's going to get something a little bit more complex, but we're going to talk about a factor tree. Now, when I make a factor tree, I branch things off, and as I branch things off, I write two things that multiply to give me that a number above. So I'm going to look at 180 and write that instead as 18 times 10. Now, I don't write the multiplication sign in my factor tree, but I know that a factor tree always uses multiplication. Now, I'm going to look at each of those numbers and keep on splitting them up into its smaller factors until I feel like I can't split it up any further because I've reached prime numbers at the end. Now, 18 itself is not a prime number, so it can be broken up further, and I can break it up as 3 and 6. I could break it up as 9 and 2. It will not make a difference to my final answer. So I'm going to break it up as 9 and 2. And when I break it up, I think, okay, are any of those prime numbers? 9 isn't. 9 can be broken down more, but 2 is. Now, to help make our factor trees easier to read, we tend to circle the ends of our tree. And I know it's an end when I've reached a prime number because prime numbers cannot be broken down further. Okay, 10 is not a prime number, and I could break it down further, and I get 2 times 5. And I think, are any of those prime? And you're like, yeah, Miss T, of course they are. 2 is, and 5 is. Now, everything that's circled should be a prime number. Everything that's not circled, I can keep on going with. So what are 2 things that multiply to give me 9? Well, 3 and 3. And I can circle those 2 3s because those 2 3s are, in fact, prime. Now, this is not where I end. A factor tree is just a way to help me break things down in a visual way, and I'm not doing this as mental math because that would actually be quite tricky. But it is not my answer. Because if I'm looking at the question, it says convert each number from standard form, which the 180 was, to exponential form. And the factor tree is not in exponential form. It's just a strategy to help me get there. Now, how I'm going to write 180 as exponential form is I'm going to start by looking at all my prime factors and writing them in order from smallest to biggest. So my smallest of my prime factors is 2, and I have 2 of them. So I'm going to write 180 is the same as 2 times 2. But that's not all, because I also have times 3 times 3, because those are my next smallest prime factors in there. And then I, of course, have times 5. So I am just writing this out as a multiplication statement, but specifically in the order of smallest factors first, and I'm writing it all multiplying together. And if I did do that multiplication, I would, in fact, get 180 as the answer. Okay? And if you don't believe me, you can try it, but it is true. Now, this is still not an exponential form because I don't see any exponents up in here. However, I can't write it as a single power because I don't have the same number only repeating in the multiplication. But I do have 2 2s, and I can write 2 times 2 as 2 to the power of 2. And I do have 2 3s, and I can write 3 times 3 as 3 to the power of 2. We only have 1 5. And so that's just times 5. I don't write the secret exponent of 1 on the 5. I know it's there, but it doesn't actually provide me anything useful. So I'm just going to leave it as this. Now, having my final answer as 180 is equal to 2 to the power of 2 times 3 to the power of 2 times 5 is the exponential form we were looking for. Okay? That was our goal. That is how I can adequately represent a number from standard into exponential form. Okay, I'm going to pause the video. I want you to try B and C and D on your own, and then I want you to unpause and come back. Go. And welcome back. Okay, I'm going to do the next ones. You might have broken things down differently, and that is okay. But you should still get the same final answer as I do, because a factor tree will always lead to the same final answer if done correctly. So if you get a different answer, it's likely because you made some sort of multiplication mistake. So if I had, for example, 25, I know that's 25 times 10. No, it isn't. That's 25 times 100. But if you had made that multiplication mistake of saying 25 times 10 gives me 2,500, instead of 25 times 100 gives me 2,500, that's where I would have a difference in my final answer, is if I made some arithmetic mistake proceeding down the line. So always be careful, double check what you're doing, take your time, but that's where you would get an inconsistency. Okay, 25 is not prime, but it does multiply 5 and 5 together to get me 25, and both of those are prime numbers, so I'm going to circle them. 100. 100 breaks down. I'm going to write it as 10 times 10. You might have written it as 2 times 50. That is okay. Gives you the same final answer, because when I break things down, 10 breaks down into 5 and 2, which means 10 also breaks down into 5 and 2. And I get 5s and 2s all to be prime. Again, this factor tree is not my final answer. It's just a strategy to help me get to the final answer. So I'm going to write this as multiplication in order of my smallest ones first. So I have 2 times 2. And then moving up the line, my next biggest ones are 5s, and I have 4 of them. Times 5, times 5, times 5, times 5. And I can write that instead in exponential form of 2 to the power of 2 times 5 to the power of 4. And again, I always write the smallest numbers first, because I want my smallest bases to come first in my exponential form. That is the standard form that we accept in math, which would be a communication error if we had swapped it. So I'm always writing it with the smallest base first. Okay, the next one. The next one, you might look at 576 and go, I don't know how it breaks down, but I know it's divisible by 2. So I'm going to roll with divisible by 2. And 576 divided by 2 is, in fact, 288. And if I don't know this off the top of my head, I could use short division or long division on the side if I needed to. 2 is prime, but 288 isn't. I can keep on splitting that up. I'm going to split it up as 2 and 144. 2, again, is prime. 144 isn't. Now, instead of splitting things up by dividing by 2 every time or breaking it up as 2 times something, the bigger your factors that you think of are, the shorter your tree ends up being. So yes, I can do this as 2 times 72, but I also can do this as 12 times 12. There are other options for me as well, but all options should lead to the same final answer. 12 breaks down further as 4 and 3. And in these cases, 3 is prime. 4 is not. 4 breaks down as 2 times 2. And I get a tree that looks something like this. And again, it's not necessarily what your tree looks like. It's all about what you get for that final answer, because trees can look different but still get the same final answer. Okay, my smallest prime number is 2, and I have 6 of them. 2 times 2 times 2 times 2 times 2 times 2. And then I have 3 as my next smallest prime number, and I have 2 of them. And I'm always writing them from smallest prime number to largest prime number, all multiplied together. Okay, now to write this in exponential form, I have 6 2s, so I have 2 to the power of 6. I have 2 3s, so I have 3 to the power of 2. And this here is the exponential form of the number 576. Okay, my first 3 examples here all were the exponential form of numbers that aren't really nice to put in exponential form. They're pretty complex. I get it. Now, if I look at 81, you might be like, hey, Miss T, I can already do this because we looked at this on the previous page. I wanted to include an example where a number was in standard form, and I wanted to write it in exponential form with the smallest possible base. And yes, you might look at 81 and go, that's 9 squared. And that's true. That's totally true. But it's not necessarily in the smallest possible base. And we can always get the smallest possible base by using prime factorization. So yes, 81 is 9 times 9, but 9 times 9 breaks down to 3 times 3 and 3 times 3. And all these 3's are prime. So 81 can be written as 3 times 3 times 3 times 3, or as 3 to the power of 4. This will give me an answer with the smallest base. So just real quick backtracking. When I look at the previous page and I'm given a number like, 64, and I'm like, oh my gosh, I know 8 squared is it, but I don't think 8 squared is the smallest, the power at the smallest base. What do? I can break things down and check. And I can use a factor tree to do that all of the time. To get to that final answer. Right, 64 is actually 2 times 2 times 2 times 2. Oh my gosh, I ran out of room. Times 2 times 2, or 2 to the power of 6. So always a possibility if I'm forgetting off the top of my head what that number is, that standard form is as exponential form, factor trees will always help. And that's what it says in this bubble here. Now, there's practice that follows. Please work on that practice. Try it out. And I will see you hopefully tomorrow. That is for homework. I hope you have a great day. Goodbye.